Okay, there we go. Check that audio. Yep. Okay. Hit the wrong button. Sharing. Okay. All righty. Looks like it's about time. Whoops, hit the wrong button again. There we go. About time to get started. Just gotta delete this junk off of my thing. Okay, we're in business. So here's what we were talking about last time. We were talking about visualizing functions, different ways to visualize functions. And really one of the big point takeaways is don't put too much stock in graphs. Don't assume that every picture you see is a graph. It's very likely not to be, right? But nevertheless, a graph is a useful picture, and we talked about what a graph is. Roughly speaking, it's where you set a new variable equal to the value of the function, or said differently, it's where you combine inputs and outputs all as coordinates of points on your picture. And we went through several examples. I mean, I like to point out this is an important picture of a function right here. This is not a graph really in any sense, right? And it's very limited in what it can show as well, right? But nevertheless, it's a picture we can draw where a graph is not possible, right? So it's very important that we be able to understand pictures like this as well. Level sets, we talked about level sets. This is where instead of setting the function equal to a new variable, you set the function equal to a constant. And we saw several examples of this. Such as these circles here, level sets of that function. And then I made the observation that even though graphs and level sets are different, you can see right there in the equations, right there, the equations are clearly different. If you were to take a horizontal cross section of the graph and compare that with the level curve, those are the same. I mean, pretty much the same technically. If you, the level sets live in R2 in this example. The cross sections of the graph, well, the graph lives in R3. Their cross sections live in R3. So you do have to technically take these cross sections and project down into the XY plane to get the level sets. But anyway, as far as the equations go, they're the same. Okay. All right. Familiar? I hope everybody remembers all this stuff. Okay. And then we ended with this example. So I think this is a really important example. It shows all the different, well, 3 different ways anyway, that you can use algebra to describe a curve. And very often, this is what we do with algebra. We have some geometric object, here a line, and we want to get some algebra on the page so we can start doing some calculus and compute some stuff, right? And well, which algebra should we write down? And it's important to recognize that this line, while it is a graph of that function, it is in a different way. It's a level set of that function, and it's parameterized by that function. All of these are describing the same line with different algebra. So when it comes time to do some calculus and take some derivatives or what have you, right, you got to make sure that you're looking at the correct function to do the calculus with. And if you do the right calculus with the wrong function, you're going to get wildly wrong answers. And if you want to know the slope of that line, well, you take the derivative. But the derivative of what? You take the derivative of the function whose graph you're looking at, because derivative equals slope is the calculus of graphs. And it is absolutely not the calculus of level sets. So, you take these functions here, g and x. Come on, erase. There we go. These 2 functions here. What are their derivatives? Well, it turns out that even though we don't know what the derivatives are yet, we absolutely can talk about derivatives of these functions. They do say something important about this picture, and it absolutely is not the slope. Right? So there's a whole new calculus that we're going to discover for these constructions. Okay. All right. I think, yes, question.
So up above, when you showed the level set
Yeah.
equation,
Uh-huh.
I know we talked about setting the equation equal to constant.
Yep.
So would we set the g of x, y?
Yeah, that's right. So that's right. So this phrase, a level set of, means that whatever function follows, here it is, right? A level set of means that I'm going to take that and set it equal to some constant. And so is it the case that I can set, this function equal to some constant and recover this equation? Yeah, sure. Right now, and in fact, there's a very particular constant. It happens to be 6 here, right? But yeah, absolutely. Does that answer your question?
Yeah.
Yep. Anybody else? Okay. All righty. Okay. So yeah, so that's where we were last time. Let's move it along. I think this is a really nice observation. Every graph is also a level set. Now, importantly, a level set of a different function. This is not saying you can use graphs and level sets interchangeably. Of course not, that'd be silly. But if you have a graph, so here, for example, is a graph. I know this is a graph because I can see right there, one of the variables has been solved for, right? So that, I've set this function equal to a new variable y, however you want to say it. This being a graph, right? I can do some absolutely insignificant algebra here, by which I mean, well, it's easy, but it doesn't do anything. This is perfectly equivalent. Nothing happened. I'm not changing anything there. These are morally identical equations. And yet, what I end up with as a result is now a new equation, which is clearly written as a level set of something, because I've got something being set equal to a constant. What is it that I'm looking at a level set of versus what had I been looking at a graph of? Oh yeah, they're totally different functions, right? Here I was looking at a graph. Oh, let me use a better color. I was looking at a graph of that function in light blue, right? It's called f. It has n inputs and 1 output. That's the function I was looking at the graph of. This function right here different function, call it g. It's got n+1 variables. Y is an input variable for the, oh, look at what I did. I used the same color. I was trying to contrast these. Sorry. Let me circle this with a better color. This function right here. Y is one of the input variables for this function. There are n+1 inputs. It has a totally different formula. Right? That's the function whose level set I'm looking at. Nevertheless, that graph of that function, clearly identical per the green algebra to a level set, a particular level set of this other function. Okay. So this is a, arguably just kind of throwing terminologies around. Why would we care about this? Well, because sometimes you have a graph given to you, right? Sometimes you are looking at that algebra. And yet the calculus of level sets sure would be handy. The calculus of level sets, maybe the thing that you need geometrically is something that's just not part of the discussion of the calculus, but it is absolutely just immediately given by the calculus of level sets. Well, you cannot use the calculus of level sets on that function in regards to this question because you're not looking at a level set of that function. So you'd have to change it first to this new function. And then recognizing that you are indeed looking at a level set of that function. Now the calculus of level sets applied to the new function g gives you what you want. And this is going to absolutely happen not too terribly far in the future, of course. And it's just a part of life in doing multivariable calculus. Okay, so let's see this in action. Not the calculus part, of course, we haven't done the calculus yet, but suppose you're looking at that equation right there. This is a particular surface that we're going to be able to describe confidently by the end of today's lecture, if I go at a good pace. This is a graph, written as a graph. But I can also view it as a level set. And so just, this little innocent little algebra doesn't look like anything significant actually happened. But having done so, I can say phooey on this function. Let's look at that function right there. This G function, it's a function of 3 variables. It's got X's, Y's, and Z's in it. And I am looking at a level set of that G function. So I can use the calculus of level sets. All righty. Yeah. Sadly, doesn't go the other way. It'd be nice if every time we had a level set, we could say, hey, it's a graph of this other function. It just doesn't work. Easy counterexample here. Look at this. This is clearly a level set right there, right? X squared plus Y squared equals 1. That's a level set of this G function. There's the curve, right? No tricky algebra there, very familiar. And yet this is not a graph of anything. It's not a graph because I can't get it into the form y equals or x equals, right? You cannot solve for x or y, by which I mean, to be fair, when I say solve for here, I'm saying solving for the unique required value of one of those variables given the other. So what you can, of course, do is solve that, X must be one of 2 possible values or Y must be one of 2 possible values, not what we're talking about when we're trying to make something a graph. Okay, so you can't solve for X or Y, so it's not a graph. All right, how are we doing? Everybody happy? Yes.
Why do you use that like inverse notation?
The what notation?
Like the G inverse?
Oh yeah, so this is just one of the notations for level sets. Let me go back to that page. Yeah, so I use F inverse, and this is very standard, by the way, because you're fixing an output. This thing that we've got, this thing here is an output value for the function, and the set that I'm trying to describe, it's the points that are inputs that give you that output. So it's like you're kind of moving backwards through the function.
Okay.
Yeah. Great. Anybody else? Okay. All right. Okay. So here's a neat little fact of algebra. Algebra, geometry, depending on kind of both. Certain curves that are readily identifiable, I said curves, I mean surfaces. Certain surfaces that are readily identifiable at a glance are rotationally symmetric around an axis, and that is tremendously valuable information when you're trying to draw pictures of them. So here's the observation. If X and Y appear in that equation only as part of this form, square root of X squared plus Y squared, I claim it's got to be rotationally symmetric around the Z-axis. Now, let me say that a little bit differently. An alternative version of this, if the cylindrical equation has no thetas, right? If you think about it, if X and Y appear only as part of, well, what is in fact exactly R, well, then the X's and Y's all turn into R's, and then you're just left with R's and Z's. Namely, there's no thetas. Right? So we talked previously about this alternative point of view here. If there's no thetas, well, that means all the cross sections off of the Z-axis all look exactly the same. So it's rotationally symmetric. Same deal here. This is just another way of saying that same thing. On the assumption that this is kind of a rectangular version of that same point. If the equation is as described, well, these 2 points Sure, they have different X's and different Y's, but X and Y aren't really in the equation, or at least not by themselves. The point is they're going to compute the same, well, what we know is R. And they're going to compute this. Well, they are, in fact, they have exactly the same Z's. And so they're either both on the surface or they're neither on the surface. They're the same in terms of how they relate to the surface. So same idea, really. Okay. All right. So where that's useful is that you know, again, if you have a something that is a rotation, if it's rotationally symmetric, then it is a rotation, and that means that you can look at any cross section, and then everything else is just your imagination rotating that around that axis. So let's see an example. Let's look at that equation. Right now, I previously made an assertion that this is a bowl. Let me go back to where that is. Yeah, here. I just asserted that that graph looks like that. Now I'm going to show you how I know. Whoops, a couple pages forward. Here we go. So this equation, X and Y appear only in the special form, or if you prefer, the cylindrical equation, the cylindrical version of this doesn't have any thetas in it. Take your pick. That being the case, I immediately know that this thing here is rotationally symmetric around the z-axis. If it's symmetric around the z-axis, I can look at its cross section in any plane that I like. I'm going to pick the plane x equals 0. Honestly, the reason I like the x equals 0 plane is because when we draw three-dimensional pictures, we're kind of looking straight at it, as it were, right? I mean, if I were to, I could take y equals 0, but then I'm kind of looking at an angle, and it's just, you know, geometrically harder. So let's use x equals 0. In the plane x equals 0, right? Just plug in x equals 0 into our equation. It turns into z equals y squared, which is really easy to understand. That's just a parabola. Everybody see what happened there? All right, well, it's a rotation of a parabola. And geometrically, that's in a really sort of, you know, straightforward thing to understand. I imagine, you know, rotating that parabola around the z-axis, and it gives me the bowl-like shape that I drew previously. Yes.
So before you said that it has to be in the fourth root of x squared plus 1.
Yeah, but okay, that's right. But it is, because this right here is the square of square root of x squared plus y squared. Yep. Anybody else? A little bit of lingo. This surface here, let me get rid of my mess here. This surface is called a paraboloid. It's just language, terminology, but that's what we call it. Good thing to know. It's written in the book as well. But there are other kinds of surfaces that you can draw conclusions about with this argument. So let's take this one here. What does that surface look like? Step 1, notice x and y appear only in the given form. So therefore, it's rotationally symmetric around the z-axis. Step 2, let's pick a plane. Now, just to mix it up here, I'm going to use the plane y equals 0. I could have totally used x equals 0. I'm just, you know, being flexible. Right, so here we let y equal to 0. Fine. Plug that into the equation. The equation turns into this, which of course, easy to understand. Now you do have to flash back to high school algebra and remember which way hyperbolas go. And it's easy to get that mixed up. So make sure that you're all straightened out and polished off on that particular thing, and you just got to think it through, right? But punchline, we know what those look like. We get that hyperbola. And I know that my surface that I'm looking for is a rotation of this around the z-axis. And so I just imagine rotating, and it makes this kind of I don't know what to call that, that thing there. Well, I don't know what to call it other than the mathematical terminology, hyperboloid of one sheet. Everybody okay? Yes.
So when we chose, for example, the paraboloid to do the cross section for x equals 0.
Yep.
How do we know to use that and not like x equals 2 or some other number?
Oh, well, yeah. So the great question. So, you know, how did I know to use x equals 0 as opposed to x equals, you know, some other value, you know, further over here? Because the argument that I'm making is, you know, I know that it's got a rotational symmetry, and specifically that's around the z-axis. So geometrically, I can only argue that I know what something looks like if I'm rotating around that axis something that includes that axis. Otherwise, it turns into a really hard geometry problem. I mean, you could study what it looks like in here, but then how that relates to the actual surface is just not that useful.
So we can also do y equals 0.
Yeah, you can use any plane that you like that contains the rotation axis. So you can use x equals 0, or you can use y equals 0. Or you can, if you wanted to get real weird with it, you are welcome to, I suppose, use an angled plane like that. But anything, it's got to contain the z-axis if you want the result to be useful. Yeah. Yep. Anybody else? All right. Really valuable method. I wish the book spent more time on this. I think this is really nice. Okay. Now, there are analogous arguments that can be made for rotations and symmetries around other axes. And I'm going to leave those for y'all to think through on your own. It's a good practice problem to take, you know, the argument that we made here, right? And kind of, okay, well, what if instead of x and y, what if it was x and z? Or what if it was y and z? And you're going to get a different picture. You're not going to be able to sort of lean on the convenience of the existence of cylindrical coordinates that, you know, give you that alternative point of view. Anyway, for example, suppose you're looking at this equation. Now, very importantly, let's recognize x and y as they appear in that equation, not in the appropriate form. And there is no sort of like funny business I can do with, you know, rewriting and algebra and parentheses and stuff to make this actually, you know, some function of x squared plus y squared. You just can't. Okay, but what I can do is kind of move the algebra around a little bit and rewrite it like this, and then recognize that y and z appear only in that special form. So I claim what's going to happen when you think it through. And again, I want everybody to do this on their own. It's good little, you know, mathematical weightlifting. Because y and z appear only in the special form, this is rotationally symmetric around the x-axis. So draw better. So that's going to be our rotational symmetry. We're going to make an argument about rotating around the x-axis. Now, what am I going to rotate around the x-axis? Let's see here. I can pick any plane that contains the x-axis. Now, so I could take this one, which is what I'm going to do because it's convenient, but totally free. If you want to take that one right there, y equals 0, totally fine. Go for it. The algebra won't be significantly different, whatever you want to do. And again, if you're really just a glutton for punishment, if you want to try to think it through on that plane, you can, but I don't advise it. So looking at this plane, that's where z equals 0, which I can plug right into this algebra. I guess I'll plug it in there. And this algebra then turns into that, which again, hyperbola. Familiar, right? High school algebra that we get. And this is in particular that hyperbola. And again, flashbacks to algebra 2 or whatever they call it these days, and make sure that you're good with that. Okay, so reminder, our surface is rotationally symmetric, ergo is a rotation. It is a rotation, in fact, of this curve. And when you rotate that curve around this x-axis, you know, the geometry is a little bit different, but you get It's really hard to draw, but it's I like to think of this as two contact lenses that are like pointed looking toward each other. This is what I call the staring contest, right? But mathematical name, this is a hyperboloid of two sheets. So it's still a rotation of a hyperbola, just kind of around a different axis, and so we get a different shape. Everybody happy? All righty, good deal. Okay, so deformations. Let's see here, let me do it like this. So very often it's going to be that we're looking at an equation, something like that, for example, where there's x's and y's, but the equation that I have has some weirdo constant in it that makes it not exactly the same as something that I've seen before. And I guess I could rethink entirely from first principles, what this equation is, but wouldn't it be nice if I could relate this to something I already understand and figure it out from there? So here's the big idea. Let's notice that this equation is what you get when you start with this equation that I totally understand. That's a sphere, right? Good old sphere, easily recognized, highly familiar. And it's what I get when I take that equation and every single place in that equation where I see a z, I replace that with 2z. Yeah. All the z's get replaced with 2z's. Now, different equation. It's going to have a different surface. Sure. What's the relationship, though, between these surfaces? And I'm going to just kind of think through the example of a particular point. Let's think through this point right there, which has coordinates 3, 4, 12, and it's not hard to check that that satisfies that equation. Plug in the numbers, and it works. And of course, dare I say, obviously, of course, it's not going to satisfy that equation. That equation's different. In fact, you can see exactly how it fails. It fails because the 12 that went into there to get squared, when it goes into there, it turns into a 24 before it gets squared. Well, that's way too big. It's just that 2 messes it up. But seeing what goes wrong in that algebra, you can say, okay, well, yeah, but now let me sort of smart alecky move. How about, phooey on that point, let's just take this point where it's a 6 instead of a 12. That 6 is wrong, and well, the 6 is something that's not what I want to square, but but the 6 gets multiplied by the 2 and turns right back into the 12 that I had before that worked. And sure enough, that point works. So the big trick here is to observe that if something happens to the algebra, if you replace, like I did here, all the z's with 2 z's, all you have to do is kind of undo that with the points. Right? In the algebra, I included an extra factor of 2. So in the solutions, I should take out a factor of 2. And then everything kind of goes through. Or the way I like to say this is that whatever you do to the variable in an equation, the opposite happens to the surface. Right? All the z coordinates get cut in half in response to the extra factor of 2 being put in front of all those z's in the equations. Everybody on board? This is, a little sort of like, arithmetic and smart alecky move, right? Okay, so nice punchline then is, well, I already understood that this was a sphere. So what is this new surface? Do I have to think about, cross sections and rotations and kind of think it all through? No, I could just say, oh, this is, yeah, it's a lot like a sphere, but all the z coordinates get divided by 2. So it's like I've squished down, and now I have a squished sphere. This is called an ellipsoid. I don't have to really do the whole argument again. Okay. All right. Which is good, because now while this one here, yeah, technically this is a rotation and I could go through and do that argument, that won't always be the case. And so, for example, let's suppose I wanted to understand this thing right here. If A, B, and C are different numbers, this equation, here, let me go ahead and zoom back in. This equation right here, it's not a rotation of anything, because the factors don't work out, and X and Y and Z, X and Z, none of those pairs appear only in that special form. It is not rotationally symmetric. So how are we going to understand this thing? And well, really not that big a deal. I can just observe that this is what I get when I start with the unit sphere, which I totally understand, and recognize that every X gets replaced by exactly X over A. Every Y gets replaced by exactly Y over B, and every Z gets replaced by exactly Z over C. So I've done 3 deformations. This surface I'm trying to understand is the result of taking a sphere and doing those 3 deformations. And what are the geometric deformations? Well, they just undo, in some sense, what I did in the algebra, right? So the X kind of gets divided by A. Okay, well, then all the X coordinates have to get multiplied by A. So instead of having it intersect at 1 on the X-axis, it's going to intersect at A on the X-axis, just undoing what we did in the algebra. Everybody's good? So very, very powerful. Again, you know, minus this, the rotation argument doesn't help us. What do you got there? It's really hard to say. Couple more examples, and I'm going to leave the details for y'all to work through on your own. Pretty straightforward arguments, but we already know this is a paraboloid. Well, then this is what you get when you take that paraboloid and kind of stretch it out in a couple of different directions. And no surprise, this is called an elliptical paraboloid. Okay. We already know that this is a hyperboloid of 2 sheets. We went through the rotation argument on that. So what is this thing over here? Well, I mean, you know, it's just a stretched out version of what we already know. So it's a, you know, deformed in different directions. It's still a hyperboloid. It's just now it's an elliptical hyperboloid. Because you might say, all of the circles that were in here got stretched out to become ellipses in here. Okay. All right, so now again, I've left a lot of blanks there. I want you all to take the time to go through, fill in, make sure you think it through. And a lot of these surfaces are in the book as well. The book does take a different point of view on why. Yeah, compare and contrast, see who's you like better. Okay, everybody good? Okay. All righty. Okay, so on to calculus. Week 4 in a course titled calculus, and we're finally going to do some calculus. So we're going to start with a derivative, of course. And the first thing I want to recognize is there are actually lots of different kinds of derivatives. So this is a distinction between multivariable and single variable. In single variable, there's a derivative. That's pretty much it. Right? So there are like 4 or 5, you know, morally different kinds of derivatives in multivariable calculus. And so we're going to go through and talk about all of them eventually. And of course, it'll take us a little bit of time to do that. But they are all qualitatively different. They're connected in different ways, related in different ways. They are all qualitatively different, but they all have this one unifying feature. And I think this is really important to recognize. And I want everybody to, you know, I want this to be the cornerstone of your point of view on multivariable differentiation. All multivariable derivatives relate input changes to output changes. Now, hopefully this smells familiar from single variable calculus, right? I mean, you know, we think of the derivative as being a slope, perhaps, but you recall that a derivative is, in that point of view, it's what you multiply by dx to get dy, perhaps, right? But so it's a relationship. It's something that allows you to connect, appropriate to the context, an input change and an output change. Okay, so be on the lookout for this unifying feature and all that we will do going forward. Okay, so partial derivatives is the first kind of derivative we're going to talk about. There's a lot of great reasons to start with partial derivatives. One is they're super easy to compute. So it's a nice kind of friendly first step. Also, they are very easy to relate to single variable derivatives, which of course y'all are extremely familiar with, single variable derivatives. So that's a good reason. And the third reason that I start with partial derivatives is because the book does. And I emphasize that's actually a big deal, right? The fact that the book is doing it this way. Were it not for that, if the book didn't make this choice, I wouldn't either. And in fact, in my own book, I don't start with partial derivatives. I think, all else being equal, there's a different point of view on derivatives that ultimately I think is better, but that's highly subjective. But point is, in this course, we're using this book, and I don't want to digress that much, deviate that much from the book's point of view. So anyway. Okay, that said, and I've already kind of, in this discussion, already kind of made this point, but don't hang your hat on partial derivatives as being fundamentally how you should think of derivatives. I really think that's not right. And in fact, I think the book agrees with me on this. I mean, I'll comment on that later. But the partial derivative, I want y'all to think of this as, again, kind of a first step. It's something to do. We start pulling on the thread there, but ultimately it's a tool that's useful for certain particular purposes, but it's ultimately not what a derivative is. So you've been warned, and you're going to hear me complain about that a lot throughout the rest of the course. So here's how you compute partial derivatives, and it's a cheap trick, really. We've got this multivariable function, all these different input variables. I don't know how to deal with all those input variables. So I'm just going to pretend most of them are constants. Right? Cheap trick. I'm just going to say, I wish those were constants. So you know what? I'm going to say they are constants. Okay. Cheap trick. Highly limiting then in terms of what we can actually conclude from this. We're playing make-believe. And there's a price to be paid on that, right? Okay, so all the variables are constant except for one of them. That one variable is going to remain viewed as a constant. It's going to remain viewed as a variable, excuse me. And so what I have then is, instead of having a function that has a bunch of variables, I have a function that has a bunch of constants involved in a formula involving one variable. And that is a single variable function. So that's the first step, is pretend everything is a constant except for one variable. We'll talk later about what all this means geometrically and stuff like that. Next, now that you've got a single variable function, okay, well, I know how to take derivatives of single variable functions, so go ahead. So we're literally going to take the derivative, pretending, well, let's say it this way, absolutely ignoring most of the variables. Okay, now notation before we start computing stuff. This is the notation that you'll, anyway, this is, I'm gonna say the first notation that we'll talk about. It looks a lot like the Leibniz notation from single variable calculus. Just be aware that that symbol right there is not the same as a D. It is importantly different, and if you write D, it's wrong. The D means something. That's not what that is. So do be very careful. A lot of students are kind of fast and loose about that. Oh, who cares? You know what I meant. No, you really got to write it differently. And side note, this is another one of those situations where there's a brand new symbol that you probably don't have in your handwriting repertoire. So this seems silly, but it's probably a good exercise to just kind of think through, okay, how am I going to make this symbol? Pretend like you're in second grade again and, practicing how to make your A's and your B's. Well, now you got to practice how to make this. So, silly, but it has to be done. Likewise, it's not the Greek letter delta. You can't, so the Greek letter delta kind of comes back over at the top. That's not what this is. It means something different. Okay. Another notation for partial derivatives. This is one that's kind of most reminiscent of Newton notation. Of course, Newton notation for single variable derivatives is the prime, right? We say f prime. Well, here I can't say f prime because that doesn't indicate which of these several variables am I pretending is the only one, right? So prime doesn't make any sense. So, but you can just kind of make it a subscript that this is the leanest or most streamlined, you might say, notation for a partial derivative, just a subscript indicating which variable you're taking the partial with respect to. Okay, with that all said, let's actually do it. I'm going to compute this ugly partial derivative right here. Yikes. All right, look at all that ugliness. There's three factors. I'm probably going to have to use the product rule here a lot. So we're jumping in right into the deep end. But wait, not really. Don't forget that x and z are constants, right? We're taking the partial derivative with respect to y. That means we're going to pretend y is the only variable. All the other variables are constants. X and z are constants. And that means that all of this, or I'll just do it down here, all of that is constant. All of this over here, there's no y's in there. All of that is constant. So what I really have here, what I'm taking a derivative of is y squared times a constant. Great, big, ugly, scary constant, but constant. So yeah, the constants do what constants do. They just kind of come along for the ride. Nothing really happens there. And the action of this question, taking the derivative of y squared with respect to y, gives me 2y and game over. So partial derivatives are really easy to compute, right? I mean, they're the easiest derivatives in any context to compute as a rule. Even easier than single variable derivatives, because in single variable derivatives, you don't get to just say, you know what, I'm going to pretend this is a constant right here, right? Like you can here. Okay, pausing. Questions? Everybody's good. All right. So a couple more examples. We'll start off with this one here. And again, this function looks like a really nasty function to take a derivative of. But importantly, got to keep your eye on what is the variable. So here, x squared is the variable. That means that y is a constant. That means that this whole exponent is a constant. And so what I have here is a simple function of x to the power of a constant. And then it's just that whole, bring down the n, subtract 1 from the exponent, the familiar old rule. And the first time you do this, it's going to feel wrong. It's going to feel like, no, you can only do that when that's a constant. But it is. So totally fine. And then, of course, chain rule and all that. Everybody happy? Same deal with this next example. Where now here I'm taking the partial with respect to z. That means that's the only variable involved, and that means that all of this is constant. So even though this looks like a much more complicated thing, this is k to the power of z, morally. Right, and so it's just you take the derivative in the usual way, and this, of course, is what you get. Everybody remember that old rule from single variable? Okay. All right. By the way, side note, I've mentioned this before. I'm sure I will again. Single variable calculus proficiency is assumed in this class. So I'm aware of the fact that for some of you, maybe it's been a while. Even worse, of course, for some of you, single variable calculus was a COVID learning experience. Look, if your single variable calculus isn't really kind of where it should be, that's something that does really need to be polished up. Improved, right, perfected, really as soon as possible. So we are going to assume that this kind of stuff that you're good to go. Okay, so if you need to, if you're not quite where you want to be, then you have to take the initiative and do that stuff. Okay, so you can see one of the big reasons why we like these things. They are easy to compute. And we can almost kind of see that they're easy to relate to single variable derivatives because, in fact, we're kind of computing them as if they are single variable derivatives. What we don't yet have is any reason to believe that any of this that we're doing is useful, right? I made up a sure does make my life easy set of rules. It verifiably does make my life easier in terms of computing stuff, but what does this mean? Have I just made up a bunch of nonsense? Did I just decide that, oh, hey, I got an idea. I'm going to invent a new kind of multiplication where like 4 times 7, let's just make it 47. Wouldn't that be convenient? Right? So you can make stuff up, but if it doesn't mean anything, if it doesn't relate to geometry or the physical world or something important, something useful, then it's just made up nonsense. So I have, as of this moment, not given you any reason to believe that this is useful at all. Okay. All right, so let's try to make it a little bit useful. And ask, what are the geometric interpretations of this? I emphasize it does depend very much on what kind of a picture you're looking at. If you're looking at a level set, if you're on the level set kind of picture, what does the partial derivative look like? Well, it's going to be very different than if you're looking at a graph. They're totally different pictures, totally different constructions. And so the derivative, this partial derivative, will interpret totally different ways. So we're going to start by looking at graphs. Again, because it's easy, because it's familiar, and because the book does. But there are other interpretations in different contexts. And so make sure to, we always have to be careful to not overinterpret. Okay, so we're looking at a graph. Graph means I've got something equal to z. The graph of this function is a surface, something like that. Okay. So I'm going to ask what the partial derivative is, in particular at a certain point, which is going to, if you think about it, it sits under some point that's actually on the graph. So at that point on the graph, I want to know what the partial derivative is, in particular, partial derivative with respect to y. Okay. So I'm just going to go through the process of how we compute it and make geometric interpretations as we go along. First step, let's see here. Well, I'm just going to scroll down here. First step in taking a y partial is to set all the other variables equal to a constant. Well, there's only one other variable. The only other variable is x. So y is going to remain my variable. X, I'm going to treat as a constant. The point I'm looking at has x equal to a. It's equal to a there, and it's not allowed to change. That means I'm going to pretend that x is equal to a specifically for this entire calculation. All right, you're taking a partial with respect to y. X can't change. X is that constant. Cool. Now, geometrically, of course, setting x equal to a constant means whether you're taking a vertical cross section, and this is a little weird, but you're setting x equal to a constant, and so that cross section is in the y direction, and that's just the way the geometry works. So you got to keep that straight in your mind. So we have that. And I'm now, by the way, looking at the clock and realizing we're out of time. So yeah, anyway, we'll pick up here next time. Well, in fact, I'll probably go ahead and pick up here next time. Y'all have a good day. See you later. See you on Wednesday or in my office hours in a couple minutes.
Because